Hi everybody, this is lesson 3.4.4, and in this lesson we're going to look at exponential word problems. Example 1.
Okay, in this question here, we read that the number of fish in a lake on August 1st, 2012 was estimated to be 55,000. The population is projected to be 155,000 on August 1st, 2028. If the growth of the fish population can be modeled as an exponential function, find the average annual growth rate of the fish population expressed in the nearest tenth of a percent. Okay, so here we go. We're going to represent the population of fish in the lake here with an exponential function here. Now, depending on who your teacher is, you might have used different models, different notation here, so it's kind of hard to find something that everybody can kind of agree to here. So what I'm going to start with here is just y equals ab to the x. Okay, just a basic exponential function. It's got our power here with a vertical stretch in it. This seems to be a pretty standard one here. Now, what we're going to do here is I'm going to just change the notation here just to make it kind of fit with the scenario here. So what I'm going to do here is y here is going to represent our final population. So I'll put PF here. A, now in this particular form here, A would represent the y-intercept, okay? The value of the function when the x-coordinate is equal to 0. So that seems like a fairly reasonable, okay, place to put our initial population. Okay, now we don't know what the growth rate is. I'm going to put r there, but the base there, that we're going to keep multiplying by that base. That seems like the place that we would put the growth factor, okay, written as a percentage, and to the time, however many years go by here. So just to be clear on what I've done here, we're going to let PF, this is going to equal the final population, okay, PI is going to be our initial population. Okay, the R is going to be the annual growth rate. Now in this case, this is what we're looking for. Okay, and the T will be about time passed, or in this case, I guess the best way to say it is the years passed. So, based on that, what we know here is, okay, first of all, T is probably going to require the most amount of work here. Like we already know here that the initial population was going to be 55,000 and that the final population that we're projecting here is 155,000. Now the question is, what's going to be the T here? How many years have passed? Okay, well, we see in the question here that we're ending at the year 2028, but we started the year 2012, so that's 16 years that have passed since the beginning measurement was taken here. So with that in mind, we can jump into our formula here. So therefore we can write 155,000 will equal 55,000, okay, times r to the 16. Now you need to notice here, and at this particular point in this course, it's very, very tempting to want to do the wrong thing here. What we need to do, first of all, regardless of what you think you need to do, is we need to isolate the power here. So I'm going to divide by 55,000 here, and when I simplify that, when I divide both sides by that 55,000 and reduce it, I'm going to get 31 over 11 is equal to r to the 16. Now, here's where the real problem kicks in. Because of the work that we've been doing, it's very tempting to think that I'm going to use logarithms to solve this. But the truth is, this isn't an exponential equation here, okay? This is not exponential. Okay? Whoops, sorry. This is not exponential. Turns out that actually this is polynomial. Okay? So in order to solve this, what I got to do is I got to raise both sides of this to the reciprocal power. The reason why I don't use logarithms here is because the variable is not in the exponent, it's in the base of this power. Okay, so I'm going to take the 16th root of 31 over 11, and that's going to be enough to isolate the r here. Now, I might think of doing the plus or minus 16th root here, but I understand when I do this problem here that the negative really doesn't make much sense in context. And when I do that, I get that, okay, that the R here is basically or approximately 1.067. And now what this represents is this is 100% plus an additional 6.7%. So therefore we conclude that we've got a growth rate, okay, of 6.7%. Okay, again, because the R value, the rate that we found here in our equation here is 1.067. Again, that represents 100% plus this additional little bit left over, which translates to the 6.7.
Example 2.
This question tells us that a sports car depreciates at a rate of 18% per year and was bought for $70,000. How long will it take to depreciate to 20? Did I say 7,000? I meant $70,000. If I said that wrong. How long will it take to depreciate to $25,000? Now, the thing that you want to focus on here is the word depreciate. Okay, that gives us an indication of how to handle this 18%. We'll talk about that in just a minute here. So this is another situation here where we use an exponential function here to model this kind of a growth or decay. So I'm going to just jump right to this thing right here, y equals ab to the x. Okay, and now what I'm going to do here is I'm going to rewrite these variables here, which is different variables to represent values that fit in this problem here. For example, I would think here that y would be, this would be a good place to put VF. And let's call, maybe let's move over here. Let's call VF here. This is our final value. Whoops. Final value. Because A is going to take the place in this particular function here of our y-intercept. Okay, that's the value when of the function when the x is equal to 0. That probably makes sense that this would be our initial value. Initial value. B here is going to be the rate of change. Okay, so and yeah, we're going to have to play with this because I don't want to say depreciation rate because that's actually not true. We got to talk about that in just a couple seconds here. This is going to be our annual rate of change. Okay, whoops, I wanted to put a different word there. Rate of change of the value of that vehicle. Okay, and then T is going to be the number of years passed. Okay, so this is going to be R to the T. Okay, now in this particular scenario here, let's talk about what we've been given here. We know that our final value is supposed to be 25,000. Okay, and we know that the initial value here was was 70,000. Now, R, what's the R here? Well, here's the issue here. The R, okay, should refer, okay, to the, how do you say this? I guess, to the fraction of the value left over. Okay? It's the fraction of the value left over. So think about it like this. So we lose, okay, in this problem right here, we are losing 18%. So we retain 82%. And that's the number that's important. Okay, so when we come over here and talk about the R, this should actually be 0.82. Okay, so now let's put these things into our equation here. We're going to get 25,000 is equal to 70,000 times 0.82, the fraction or the percentage of the value left over, all to the T. Now in this case here, I don't know what the T is. That's what I'm looking for. I want to know how long it takes for this to happen. Okay, so the very first thing I will do is divide by the 70,000 and then reduce that fraction. And when I do that, I'll get 5 over 14. Okay, and this is still 0.82 to the T. Now in this case right here, the variable is in the exponent. Okay, for this power, we know that the base is, we don't know what the exponent is. That is an indication that this is going to require logarithms. Okay, in the previous question, that wasn't the case. The information was switched. But this one, that does make perfect sense here. So what we're going to do here, okay, so we're just going to make a big note here. The variable, okay, the variable is in the exponent. Whoops, can't see that. The variable is in the exponent. So now we will take the log of both sides. Okay, and the bonus to that, or the benefit to that, is that I get to bring the t down. So this becomes the log of 5 over 14 is equal to t times the log of 0.82. Now my goal here is to get the t by itself. So, and remember that the log of 0.82 is just a number. It's just a number, it's just a decimal number. There's nothing crazy about that. So I just divide both sides by that. So this will be the log of 5 over 14 divided by the log of 0.82. Oops. And that'll equal my t value. And when I do that, I'm getting basically 5.2. Okay, that's approximately equal to t here. So it didn't actually say what to take this to. So therefore, it reaches, it might make sense to say it like this. It reaches 25,000 in, whoops, okay, the 6th year. Now, just to explain that here, the answer that I found here for t was 5.2. Now, what that means is 5 complete years have passed and we are 0.2 of the way into the next year. But that is the 6th year. Okay, whether you're 0.1 of the way into it or 0.9 of the way into it, you are in the 6th year of the ownership of this vehicle, or in the life of this vehicle. So that's probably the best way to answer that one.
Example 3.
In this question, we're being asked to write an exponential expression that will determine the final value after n compounding periods. Okay, this is kind of pushing us in a certain direction here, of an investment of $5,000. Now, you may not have worked with this particular equation before, okay? It is possible to kind of talk about these sorts of issues here without specifically addressing this. I'm going to come right down here, and we're going to talk about the function here that makes the most sense here. This typically is asking us to use the compound interest equation. Okay? And so this is going to look like this. A equals P times 1 plus I to the n. Okay, now this is, for all intents and purposes though, this is y equals AB to the x. Okay, this is still just an exponential function, which is why I said what I said to begin with here. You might not even have explicitly talked about it as the compound interest equation. You might have just worked with this as an exponential function. However, in this particular context, in this question, this makes the most sense here. Now we just gotta, if you've never worked with this before, even if you have, it's not a bad thing for us to go back over this. What A represents here, and remember this is, although this is the compound interest equation, it's really a good way of looking at population growth. Money is like people, okay, or like living things. When you get money in a bank, and because of the way interest works, that kind of the population of the money, that grows. Okay, so think of this as a population sort of model here. So A refers to the accumulated amount. Okay, the final value, the final population of money there, if you will. P is our principal. Okay, which is our principal investment. This is the amount of money that you put in there to begin with, or it's the initial population, if you will. Okay, I is going to be your interest rate. But this is an important one here. It's not just an annual interest rate. You got to be careful on this. This is the interest rate per compounding period. Okay, per compounding period. Now, what that means is, if you're not clear, when the bank calculates the interest and adds it to your account, that's a compounding period. So if it does it every 6 months, that's the compounding period. And so then N is going to be the number of compounding periods. Okay. N is the number of compounding periods. If you want to figure out how much money you got left over, you got to know how long it's been in there, but not necessarily in the number of years, the number of compounding periods. Now, with that in mind, let's go up to the original problem here. And what we want to do is just write an equation right now to model this. Okay? Now, compounded semi-annually, okay, semi-annually means twice a year. Okay? Twice a year. Now, the interest rate that we're getting, okay, the interest rate here is per year. So we have to adjust this a little bit here. Our accumulated amount, okay, is going to be, what was our initial investment? Our initial investment was $5,000 here. So our accumulated amount is going to be 5,000 times 1 plus, okay, well, it's not 8%, okay? That 8% represents an interest rate per year, but we're compounding it twice a year, so basically every 6 months here. So you're actually only going to get 4% during those compounding periods, okay? Yeah, and then to the end right there. So what we need here is this interest rate to match this number of compounding periods, okay? So, and if you want to think of it like this, N is going to equal 2 times the number of years. Oops, it's going to run off here. N is going to equal 2 times the number of years, because if you have it in there for 4 years, that's going to be 8 compounding periods. Okay, let's try to look at this. Take a look at this next one here. Invested at 6% per year, compounded quarterly. Okay, well, quarterly. Think about what that means. Okay, it means 4 times a year. Okay, so again, A is going to equal 5,000, our initial investment. But this time what we're going to do is we're going to take that interest rate and divide that by 4. Okay, all to the power of N. Okay, and so this time N is going to equal 4 times the number of years. Oops, number of years. Okay. So if it's in there, again, if I go back to my the 4-year mark there, if I put it in there for 4 years, that's going to be 16 compounding periods. And so that's what that would have to be to represent 4 years. And then this last one here, invested at 4% per year compounded monthly, okay, with 12 months in a year. So that means this is going to be 12 times a year. So our accumulated interest, or accumulated money here is going to be 5,000, the initial investment, plus 0.08 divided by 12, all to the N. But in this case here, N has got to be 12 times the number of years. Okay, 12 times the number of years. And that's what we're looking for here.
Example 4.
In this question, we're being told that the population of gophers in a field is increasing at 40% every 6 months. Okay, that every 6 months is important. Okay, we're going to need to consider that very closely as we work through this problem here. It says presently there are 150 gophers in the field. How many gophers will there be after 12 months? Now, okay, so the growth here is going to be according to like an exponential function here. So let's take a quick look. Y equals AB to the X. But you know, like we were saying in the previous question, that compound interest equation really does work nicely as a population growth model. So let's just take a quick look here. Let's take a look at that. A equals P 1 plus I to the N. I really think, even though this isn't talking about money, it's talking about gophers here, this is actually a really good model for this. Okay? We're going to let A be the final amount. So this is the thing that we're looking for here. Okay? So A, in this case here, is going to be our final population. Okay? P, now think about the place that the P takes here. Okay? In this function right here, A would be the y-intercept, or the value of the function when x is equal to 0. Well, P is taking that same position, and as such, this is going to be our present population. Let me move inside here. Now we've got 1 plus I. Now I represents in the compound interest equation, it's going to be the interest rate per compounding period. Okay? Interest rate per compounding period. So this is going to be the growth rate. Now, we don't typically call it a compounding period, but we might as well call this growth rate per period. Okay? The reason for that is population kind of grows smoothly, continuously. Okay, when you're dealing with this in a bank situation, there's a time when they calculate and add, and that's a little bit different. And then n here, okay, n in this formula here should be the number of compounding periods. Now, this is a little different for us here because we don't have these compounding periods, it's just the number of periods. So n should be the number of periods passed. The number of periods that have passed. Now that gets a little harder to deal with here. So this might be a case where we play with this a little bit. Maybe what we'll do with this is we'll make this a little bit different. Let's change this to t over, I don't know, let's what would I say here? T over g. Okay? And the reason why I'm going to do this here, and just because I'm getting kind of lazy here and I don't want to do some of the math here, I'm going to let t be the months past, because months seems to be the units here, months past. And what I'll let be here is I'll let g be the growth period. Okay, this is our growth period. So instead of me trying to figure out the number of periods that have passed, I'll just create a little fraction up here that will deal with that for me. Now I know that in this particular case here, that growth period, because they tell me here, is 6 months. So now this equation becomes this: a equals p 1 plus I to the t over g. Okay, and again, you may have used different variables. The way you approach this is going to be different from teacher to teacher, kind of how they represent it. But basically this boils down to just being an exponential function. And all I'm doing here, and all any of us is doing, is just labeling these things differently. I like using the compound interest equation because I think it offers some insight into the way populations work here. Now, in this particular case here, okay, we know that the initial population was 150. I know that I is going to be 40%. It's a growth rate of 40%. I know that T is 20 months, and I know that the growth rate here is 6 months. So now all I have to do is plug this in. So my accumulated amount, my final population here is going to be 150 times 1 plus 0.4, or 40, okay, to the 20 over 6. And that is approximately, okay, and I say approximately because I do have to round this, 460.452 dot dot dot. Okay, now the question is, how do you round this? How do you deal with this answer when you're dealing with discrete objects? Okay, I mean, we really don't know what to do with that 0.452 blah 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 of a gopher. Now, it turns out, and I got this, I can say this quite confidently from because of a conversation that I had with someone in Alberta Learning who really made a good argument about this. The answer here, this can actually be rounded in either direction, okay? This is either, okay, 460 gophers, or you could round that up if you wanted to, 461 gophers. Now, normally when it comes to the diploma, what they will do is they will make it so that the rounding seems pretty clear. In a case like this, you could argue that you round it down because that gopher doesn't really exist, or 460 rounded up because you maybe a gopher's being born here, and there you go. Either way, both of those are acceptable. But on the diploma, typically what would happen here is this would be like, for example, closer to or above 5, and so that would naturally round up anyway, and it would be, most of us would have done it that way. So there's really no reason to be concerned about how to round this.
Example 5.
Okay, in this particular problem, we read that an air sample contains 2,000 particles of suspended matter. And each time the sample is passed through a filter, 32% of these particles are removed. Okay, we really gotta focus on that here, because we had mentioned before in our model that our model should always reflect what is left over, okay, not what's removed here. So the fact that that's being removed, that's a key, something we got to look at here. So we're being asked to determine an expression for the number of particles still suspended in the air after it passes through 8 filters. How many particles of matter are there after the 8 filters? Okay, so we got to come up with an equation here, and then we got to evaluate it here. Now, because we're taking out this percentage each time, this is like an exponential function. So let's compare this to y equals ab to the x. You could consider this like a population, but I think for the most part this exponential function works fine. And so what I'm going to do here is I'm just going to again change the variables to kind of fit my purposes here. I'm going to put a pf here. So this is going to be my, if you want to think of it this way, this is my final number of particles. Okay. My A here, as I've said a few times before, really refers to the initial situation here. So I'll put a PI here. This will be my initial, okay, number of particles. Okay, B, as we've seen before, B has got to be is the base of the exponential. It's the fraction or whatever that we're multiplying by every time here. So in this case, we'll call this the R. Okay, and really, this is just going to be my multiplication factor. Okay, it's the value that I multiply every time, and we're gonna talk about that and get that cleared up here. And then to the n, okay, n is going to be the number of filters. Now, it's important to note, based on this particular problem here, okay, that n, okay, note, n has to be an element of the whole numbers. Okay? Okay, or as some people put it here, the non-negative integers. Okay, either 0 or positive numbers. You can't have a fraction of a filter here. Okay, so just something to consider. Now, based on what we've seen here, let's start to put stuff in here. We're trying to come up with an expression for the, what was it here? For the number of particles still suspended in the air after it passes through 8 filters. Okay, so we're looking for our final here. We know that there are initially 2,000 particles of suspended matter. Now, again, remember that this is the multiplication factor here should illustrate or should represent what's left over, not what's being taken away. So if we take 32% out, we are left with 68%. Okay? This is what is, remember, this is what is left over. And then, after 8 filters would be to the power of 8. Okay? And when you evaluate that, we get approximately, what is it, 91.43, and it goes on and on. Okay? So, but just like the previous question we were talking about gophers here, because we're talking about particles of suspended matter, I mean, this is a discrete thing. We're talking about a number of particles, really. Let's face it. If you divvy up a particle, slice it like that, I mean, we're not accounting for size here. If you cut a particle in half, you've actually got now 2 particles. So this could be, okay, this could be 91 or 92. Okay, either way, those would be acceptable answers.
Example 6.
Hey, this question's a little different than the ones that we've done just up to this point here. It says a colony of 300 ants triples. See, now that's an interesting thing to put there. Triples. Its population every 14 days. How long will it take to grow to 10,000? Now, again, we're talking about growth and how the growth of the population here, and this is essentially exponential. Okay, so what I'm going to do here, though, like I've done before, I'm going to take that function, I'm going to rewrite it using different variables here. I think it's been kind of pretty clear what we're doing here. This is going to be population final. Okay, so we'll just go final population. Okay, I think we've seen this enough that the A here is going to represent the initial population. Okay, initial, population. Now the question is, what do we do about the b here? Now I used the compound interest equation before for population growth because it was it's such a good model for that. However, it's a little awkward to use when you talk about growth in terms of like doubling or tripling, where we've actually got this multiplicative factor that's larger than just a percentage here. So what I might do here in this case, I'm gonna use r. Okay, and I'll call this our growth rate, but it's going to be a lot simpler than it has been in the past here. This is our growth rate, and then we'll let, in this case here, it's got its population every 14 days. Now, just like the compound interest equation, this growth rate, okay, has got to be per period. Okay, per period. And I got to be really careful about that. So the exponent, okay, so up here, if I put an r here, I'm going to kind of cut a corner here. I'm going to make this to the t over, let's say g, where I'm going to let t be the number of days past here, and I'm going to let g be our growth period. Okay, because remember, r occurs per period. That multiplication factor occurs with every period here. Okay, so what I got to do is figure out how many of those periods pass. The exponent here, if you think back to the compound interest equation, the exponent should be the number of periods. And this is just the easiest way to calculate that. Okay, so in this particular case here, given the information here, I know that my initial population here was 300. Okay, I know that my growth rate here is 3. It's just because it's tripling. Okay, it triples. Now, what have I got here? My t, the growth period here is going to be 14 days. And we know that the final population here, we were given that the final population was 10,000. What we want to figure out is how long it took to get to that point. So let's just plug that all in. So therefore we get 10,000 is equal to 300 times 3 to the t over 14. I don't know what the t is. Now, what I got to do here first to solve for the t is I have to isolate the exponent here, or I should say isolate the power. So I'll divide both sides by 300, and that'll reduce this down to 100 over 3 is 3 to the t over 14. And again, because the variable, when we look at the power, because the variable is in the exponent, I need to use logarithms. If the variable was in the base, I wouldn't. But because it is in the exponent here, I'm going to use logs. Okay, so I'll take the log of both sides. Okay, 3 to the t over 14. And the benefit to using logs is now I can apply the log laws. This will become the log of 100 over 3. Now that's just going to be a number. I'm not particularly worried about that. But this is going to end up being t over 14 log of 3. I can bring the exponent down, which is really what I wanted. Because now I got to get t by itself. It's actually pretty straightforward. I will multiply by 14. Whoops. Sorry, I wanted to put it parentheses there. 14 times the log of 100 over 3. And then I'm going to divide by the log of 3. And that will equal my value of t. Now I go to my calculator and I get here that this is going to be 44.685 ... So that's approximately equal to t. I had to round that. So now I think about that. What that means is, okay, that 44 complete days have passed, and we are 0.685 ... into the 45th day. So therefore, okay, this occurs, whoops, on the 45th day. Should round that up.
Example 7.
This question says that the half-life of mendelevium is 258, which, by the way, this is an unimportant number. Don't try to include that in the work here. But the half-life is 51.5 days. Determine the number of days it will take for there to be only 2% remaining. Okay, well, as with everything else in this chapter here, or this particular lesson here, I should say, these are all questions that can be modeled with an exponential function here. So just like we've done before here, I'm just going to change the variables here. So I'm going to let y be pf, and this is going to be the, let's say, the final amount here. Okay. I will let a be pi, the initial amount. And then I'm going to let b here, we're going to use the variable r here. This is going to be our rate. Okay, now, rate of growth, rate of decay. In this case right here, this is more closely related to this ant problem that we just did. This is going to be like our multiplication factor. Now, actually, when we're talking about it as a half-life here, you can think of this as a couple of different ways. You can think of this as losing 50% of the material population, or multiplying by a half, or however you want to. I'm just going to write that as a multiplication factor, but recognize that that's going to be a half. And then, but remember, this is multiplication factor per period. And this is the part that we got to keep looking at here. Just like that compound interest equation, this is per period. So my exponent should then reflect the number of periods that have gone by. So we'll let t be the time passed. Okay, and this will be in days. So to the t, and then I'll put that g in here for our growth period. Now in this case, it's not so much growth as it is decay, but you get the idea. That's where that would go here. This is the amount of time that it takes for this thing to change here, and I'll divide that by g, so that this represents, the exponent represents the number of times I need to multiply by that r there. Now, what do we got to do here? Let's identify the different pieces that we've got. Now, we're not told, and this is one of the reasons why I like this question, we're not told how much was there initially, only that we had 2% remaining. So if we got 2% remaining, it makes sense to think of it this way, to think of it in terms of the percentage here. So let's make our final 2, and that could be 2 units of whatever, and our initial here would be 100. We just need those to compare so that the final result is 2% of the original. R in this case is going to be a half, because now I understand that we're losing a half. When we talk about half-life, we're losing a half here. But this is going to represent the half that remains. Okay? The half of the material that remains here. And we know that our growth period here is 15.5 days. Okay, so now we're going to plug that in. So we'll get 2 is equal to 100 times 1/2 to the t over 15.5. Okay. I would divide by the 100, okay, to isolate the power. So this will be 0.02. And we knew that was coming because it had talked about that 2%. So I should have anticipated that number showing up in there. And now, because the variable is in the exponent, what we're going to do here will be to take the log of both sides. So the log of 0.02 will be the log of 1/2 to the t over 15.5. And now the reason why I took the log is so that I can bring the exponent down. So this will become the log of 0.02 is t over 15.5 log of 1/2. And now it's just a simple matter of moving the pieces over. Remember, don't get caught thinking that the log of 1/2 is some weird mystical operation here. It's just a number. Okay, this is just a decimal number. So I just multiply across by the 15.5 log of 0.02. And then I'm going to divide by the log of 1/2. And that'll be my t value. Now I go to the calculator, plug that in. This is going to be approximately 290.658, that goes on. Okay, and so just like we've argued in the previous questions that are like this, what that means is that 290 days have passed, and I am 0.658 of the way into the next day. So therefore, this occurs on the 291st day. That's the answer we're looking for.